Hi guys, this is lecture number 6, parts design and choices. This is a continuation of the previous lecture, part 1. So we're just here to finish the unfinished part from last time. So the first part I'm going to talk is the model and encoder combos. Because encoders are provided by us, because we must make such a kit. So all you need to do is just design the model driver. There are a lot of different kinds of model drivers you can use, such as, we basically just use a MOSFET to make H-bridges, and there's a lot of ways you can make those kind of H-bridges by utilizing either P MOSFET or N MOSFET. So I'm going to introduce, there are 3 kinds of like most popular way that people use make such a model driver for micromouse. The first one is the one actually you guys are using on your kit mouse. Is pretty conventional way by using a regular H-bridge. This is an IC. So I assume you already know how H-bridge looks like. And this is called a P and N MOSFET type. And for the H-bridge, because up bridge is the top bridge is the P FET and the lower bridge is N FET. So the advantage of PN type MOSFET is because it's really easy to just use battery voltage to drive the P MOSFET on the top, and all you need to do is just have a really simple level shifter shifting from your PWM logic level to the battery supply level, so it will be completely turned on. But the only downside is because the top MOSFET is PFET, and PFET usually is less mobility than N MOSFET. Turned out it will tend to be the hottest part for the entire chip. That's what works theoretically. However, for our case, actually the H-bridge chip isn't not that hot. Plus I put a thermal polygon underneath, so it's not really hot. It's even colder than the 5 volts regulator. So this is first option. Second option is called N MOSFET type. Instead of having the P MOSFET on the top bridge, we use N MOSFET because N MOSFET has higher efficiency. But the disadvantage for that because if we have N MOSFET on the top bridge, then it will require a really high voltage, way higher than the battery supply voltage, to fully turn on. Otherwise, it won't be able to turn on. So, in order to use N type H bridge and fully turn on, the level shifter will be a special type. So this is such a chip called LTC442. It's a combo of level shifter plus a boost converter. So the level shifter is easier to understand, just shifting the for instance 3.3 volts PWM logic level to V battery, which is about 7.4 volts. Then the next step, they have a boost converter inside, boosting the battery voltage to an even higher level. For this case, it's about like more than 10 volts. So in this case, the top end MOSFET will be completely turned on. And this kind of schematic is a little bit different than H-bridge, full H-bridge, because this chip here is actually a half H-bridge. So no, it's not really half H-bridge. It's a chip have a 2 N MOSFET in one package. So we should hook up the wires to each other, make half H-bridge. And this is another half H-bridge, of course, so we use 2 of them to make a full H-bridge. And by using this way, for the level shifter, you will require extra diode and capacitor in order to fulfill the functionality for boost converter. So compared to previous one only have a 0.1 microfarad capacitor for low pass filter, and this is also needed for this one, except I didn't put it here. So for this one will require 2 components. That takes more space and more chips. However, the advantage is the N type kind of H bridge is more efficient. The third one is something probably you would like to see. It's called all-in-one type, which is just like single chip for each motor. The chip including H-bridge, level shifter, and if the all-in-one motor driver is a N type, and usually they are N type, and so the boost converter will also be included. They either use charge pump or boost converter. That's why you will see they will require some external capacitors, like one here, 0.1, connect between charge pump 1, charge pump 2, as external capacitor for charge pump, and some other capacitors will be also needed. So at least 2 more capacitors are needed. At least these are for power stabilization. So, but the advantage for this is like single chip will fulfill all the functionalities. Compare the all-in-one solution and those kind of previous one, level shifter plus H-bridge solution. Those kind of separate way, you can actually have easier to find make a MOSFET, make a motor driver with higher capabilities to allow more current to go through, to make the current allowance like way beyond your real power current consumption for your motor. But this one, for instance, like 3950, this one can only go up to 2.8 amp, even though this is much higher than your motor consumption. But it just, it's like the maximum current is just not that high because they integrate all the components inside. They have to control the heat dissipating. But however, this is good enough. So these are your three options. Encoders, because encoder is provided, and you don't really need to worry about what the shape looks like for encoder on your own PCB. So since we provide an Ego library, and then once you add that Ego library like this thing, so it reserves the ports, and all you need to do is just connect power to VDC, ground to ground, and 2 channels for each encoder because it's quadrilateral encoders to your MCU. Then that's all you need to do. And then notice, even though I put the 5 volts to supply VCC, but actually because our logic level for MCU is 3.3 volts, so we can actually supply 3.3 volts to 5 volts to the encoder. But for safety, to give a much better sharp reading, so 5 volts is preferred. Okay, user interface. User interface will take a lot of slides because there's a lot of different sections, and they're quite important to help you to do the debuggings. Okay, first is LED. LED is the most common way to, as for the debugging, and you can either use different number of LEDs with different colors to have various combinations to give you different kind of informations. For LED, probably there are 2 ways you can hook up an LED with the MCU. The way on the left is pretty much the one Okay, use the MCU piece to supply the power, then connect the resistor to limit the current, then go LED, then go ground. The other way is have the LED power by the external power source, but have the negative terminal go back to MCU. So either way works. So for the programming part, so if you want to turn LED on, for the case on the left, then you send it high. But for the case to the right, if you want to turn the LED on, you have to send it low instead. And the pro and cons, this is like, as I would mentioned, this is much easier to, not much easier, it's slightly easier to make a trace on PCB because after you come out from the MCU, then go grounds, there's definitely more ground you can find on PCB. So more ground than these 3.3 volts, of course. And but the advantage for this way is because the power, you don't really use power from the MCU, but so it reduces the workload of the MCU. Even though most of the time it will be fine, just use this way because you're not going to use like tons of LEDs, and plus you limit the current. Each one's going to take like under 2 milliamp, so it's totally fine for MCU. But either way works, just your preference, and just for information for the right one. For the buttons, okay, for button there's There are actually 3 types of buttons, but I only indicate 2. The third type will be really similar to reset button, so I'll mention that later. Let's focus on these 2 basic types. The left one is called pull up type, the right one is called pull down type. I think the one you use the most often is the pull down type, because okay, so before you press a button, so saying we want the button receive a high to indicating the button is being pressed. And before you press too high, before you press button to have the high connected to the button, you have to pull it down because the voltage is, the voltage on the pins is literally floating if you're not doing anything initially. So you won't read any correct information. That's why you need to pull it down. And the value is usually 10K to 100K. And 47K is my personal preference, and it's just we have this based on the availability of the resistor we have in the lab as well. So. But usually the size is 0402, so as long as you reserve a pad for 0402, then you will guarantee to find the value of resistor we have in the drawer. So this is the pull up type. This is the opposite of pull down. So instead of pull down initially, we pull up initially, and so your logic will be reversed as well, because if you want, when you press button, you will receive low instead of high, right? Compared to that one. So this is the programming part. It works safe, and I believe pull down saves more power, because pull up you will always have a resistor serial with power, but this one, not really. Okay, so button share with boot 0, because we have pin called boot 0 on the SM32. Mostly you don't use that pin, and it doesn't matter if it's high or low or floating. But I hook up the boot 0 with the other button pin, because when you are using this button as a normal function, you won't have anything to do with boot 0, because boot 0 is only for use the USERT 1 to download. Okay, because you guys now use the program to download code, right? But I told you there's another way you can download code through the serial port, through TXRX from PA9 and PA10. But it won't just come up like that way by default. You have to, before you power it on, you have to make a boot too high, then power it on, then release the boot 0. Then it will goes into the ICSP mode. Then you can use the FTDI board to download code through the serial port. So in order to make it high, that's why we have to hook up this to the button. But we don't want to only make a button only for boot 0. It's kind of wasted. So we share this, and they won't interfere to each other, because it will only work at their particular time. You know, the regular button will only work when it's powered on. But we need boot 0 before power is on, so they really won't interfere with each other. And I highly recommend you to have another pin hook up with boot 0, then share with one single button, because you want another, other than the programmer, you want use FTDI as the way to download code as alternative method, because some of you might have the issue that program sometimes doesn't work, right? So use FTDI. Download code is always your ultimate final solution. There's a resistor here. This is really optional. You can either have a resistor here or not, just like have a wire go through. This is really optional, but the resistor here is fully limited current for protection. Okay, Okay, reset button. So the reason we need a reset button, because sometimes we just don't really want to power off and on, and because we also have an LED display on the mouse, it also requires a reset. So if you don't have the reset, then the character left on the screen won't just disappear. It will stay there unless you power it off. And also for the Bluetooth, if you mess up something, you want to start over the whole setting sequence, and you don't want to just like power off the mouse and power on, because it takes a while for the Bluetooth adapter to pair with your computer. So just press the reset button, your Bluetooth adapter will still pair, and everything will start over. And this is typical schematic for the reset button. This is really optional, but it's recommended to have it. The value is 10K or above. And this is the basic one. You need this capacitor to here to parallel with the ground to stabilize the charge, to make a charge balance here. Make sure it's not floating. Actually, this is also the third type of the button I mentioned in the 2 slides before. You can actually make your press button in this way. If I have a capacitor connect parallel to the ground, and to prevent this terminal being floating. So this can connect to anything on the MCU. Okay, this is a buzzer. Buzzer is also really very important. I think it's even more important than the LED display, because there are a lot of cases that you literally can't, even if you have an LED, it's running too fast. You can't even see anything from the LED, because it's either running too far away or moves too fast. You can't tell which LED, which switch. So the sound is the only way you can recognize the behavior of the mouse. So the way we're doing here is use a magnetic buzzer. We're not using piezo, because piezo is kind of like it's not loud enough, basically. And so we just use simple as PWM to drive the buzzer, but supplied it with 3.3 volts, and also we need a this is optional, but I highly recommend you have it. The dial is to prevent kickback current, because for the buzzer itself, it's essentially an inductor. Once have like changing period, frequently changing current, it will generate the kickback current. And this thing will prevent that from happening to damage the power source. So the one we use on the kit mouse is actually a MOSFET, and of course I put it down. But it doesn't have to be MOSFET. It can be either NPN transition or MOSFET, even PNP transition, or even PMOSFET, depends whatever you're doing. So so you can so for your case, you can either use single MOSFET or single NPN transistor, because MOSFET and NPN is much easier for you to manipulate logically instead of P-type. And make sure the current. Okay, because firstly, before when you choose your buzzer, check the maximum current consumption, or called current rating, on the buzzer. Then make sure this MOSFET or transistor won't the maximum current will be larger than the maximum current it consumes, and always leave have loops. And also make sure you check the supply voltage range. For instance, some buzzer, can only supply maximum 3 volts, then it won't be a suitable case for our design, because we have 3.3 volts. Even though I believe it won't burn, it might still work, but just for safety caution, pay attention on the power rating. Okay, display. Display is another very useful user interface we're using. And by having just LED on and off, this thing can have a lot of information, because you can literally display the characters. I don't know how much you like the one we have on the kit mouse, and for my case, I literally use that to print out a lot of things. Well, even though we can use serial port to print out a lot of streaming a lot of data, but compared to serial port, because we use SPI for this screen, it takes much less time than the serial port. And so if you're not planning to print out a lot of data, but more like time sensitive, for instance, like speed, of the encoder speed, or something you have to like update every 1 millisecond, then printing out through the display is much better choice than the serial port. Because when for instance your mouse is running, like not like extremely fast, like running at relatively slow speed, you can still see a screen, but you definitely don't want like have a wire connected to FTDI or to your computer when the mouse is running, even slow. And you don't want use the Bluetooth, because Bluetooth won't be able to send at a really high baud rate. Otherwise, it will be disconnected. So this is your best choice. But this is really optional, because if you feel you don't use this thing that much on your key mouse, then you can totally not have it, because this is kind of expensive, costs about like $22-ish. So they will help you save a lot of budget. Okay, other than user interface, we go through the device. First is the gyro, and this is a gyro we're using on our key mouse. These two capacitor and the resistor are required on the schematic, so you will find the exact same values on the schematic. This is optional for low pass filter. And you can even put another large one parallel with it, and make sure put them as close as possible. And make sure you have two outputs, VREF and LZ. And the only thing you need to worry is because gyro's analog device is really power sensitive, so have distinguished a ground, analog ground, right? Analog power supply, and stay away from the heat source. For those for those devices who like to generate a lot of heat, for instance, like 5 volts regulator and the motor gyro, these two things will generate a lot of heat. So keep away from them, and you don't need to put the gyro in the center line of the mouse, because people might have some idea of this. Like accelerometer, you must put it in the middle, but gyro you don't, because imagine the angular velocity at all locations on the mouse are exactly the same theoretically. So you don't really need to worry about that. Oh, MCU. Because we're going to provide MCU libraries, because this is a job by myself. I really like the way it is, because it's the exact same layout on the schematic compared to the actual layout. So it tells you the exact direction for the corresponding pins. So the thing you need to notice is, because some connections are required by the datasheet, such as the pin for VCAP and VDD, VSS. For instance, the VCAP value is just being 2.2 microfarad to the ground, and you won't be able to find the value on the schematic. I found somewhere else, and the capacitor between the VDD and the VSS is usually 0.1 microfarad as a low pass filter. And for the one here, between VBAT, so you always put another additional large value capacitor before VBAT. But I put 4.7 here, but you actually only need at least 1 microfarad. So I'm just like, because I just like you simplify my solution, so I just put 4.7. I mean, as always, the larger the better. So there's nothing wrong to put larger value. And 4.7 microfarad and the 1 microfarad can be literally in one same kind of package, O6, O3. So there's no difference. And the larger one makes more likely stable. So why not? And for the analog power supplier, you have two. One 0.1 microfarad, the other one's large one. I put here 4.7 microfarad. So these are what you need to connect. Other than all the VCC, VBAT, you must have boot 0, boot 1 reset connected, because boot 1 now we connect to a button. Boot 0 we connect to a button. Boot 1 should be initially to put it down, and right here. So the resistor is optional, and the reset we showed already. And the last thing is the programmer and then the serial port. So programmer use PA13 and PA14 pins and the data and the clock pins. And for the USART, you actually have a lot of options. But but we highly recommend you use PA9 to PA10, because if you use these two pins, that's the only way you can use serial port and use that serial port to download the code through FTDI. So just use PA9 to PA10 for your serial port, and that's all you need to worry. Oh, also yeah, of course. If you don't use PA9, PA10, then there's no way you can keep using the library we provided because you're not using pins. Okay, this is a communication port mentioned here. You must make such a fashion with such a pin order. This is top view, not bottom view, okay? So 3.0, 3 volts, ground. It doesn't matter, okay, so these two parts are symmetrical, okay? For these two, for instance, this is for a programmer. It's not necessarily have to be on the left. It can on the right because you're only plugging one at a time. So just make sure your clock pin is next to ground. Your RX is next to ground. Just make sure the TX is TX pin on the MCU because the TX pin on the MCU connects to the RX pin on the FTDI board. You have to pay attention on that. They kind of like switch to each other. Yeah, I need to pin follow pin order and make sure when you're choosing because it was 2x4 plug, it's the 2.54 millimeter pitch. So don't choose anything else. So the distance between these two pins are 2.54, and the row spacing is also 2.54. I suggest you use smartphone libraries. You'll be easy to find 2x4 pin. Okay, this last page of voltage meter. I think a lot of you already know that, and I mentioned that before. The purpose is just detect voltage in order to be aware of the battery voltage in order to protect it. Just you need to notice that you have follow some certain ratio between two resistors to make sure the voltage you read here won't exceeding 3.3 volts, and not even make it close. So that's why this is the one I'm using. You can just simply make like 2-to-1 ratio. Like for instance, if you can make 67K, that's like 33K, it also works. But don't make the value either too small or too large because if it's too small, then you will draw too much current. If it's too large, then your ADC will be less sensitive. All right, that's so much for today. Any questions? You're good? This is actually pretty straightforward, I think. Yeah, go ahead.
Why is it that the capacitive trick for the button, where instead of using a pull up or pull down, like this design happen? Why does this design work?
Okay, the whole point of pull up or pull down initially, right? So just keep the charge balance. Just prevent like floating on the pin itself, right?
But you also want it to return to some value so you can see the difference between that value and the value when the button is pressed, right?
Yes.
So how does it return to V plus when it doesn't have pull up resistance?
Okay, imagine reset button. Most MCUs will make it low as a reset.
Okay.
Right? Which means it has to be maintained high.
Right.
Right? So you have to maintain high. So by having this capacitor, because okay, first you have this thing floating, it's like so powerless. This side is connected to ground, it's guaranteed to be zero.
Right.
So because the capacitor here, because like back to high school, if you have a capacitor, if you put a positive charge on the side, it will kind of generate the negative charge on the other side.
Okay, yeah.
So on the opposite hand, if you put negative charge on this side, it will generate opposite charge on the other hand.
Is it just because the reset pin is floating that there's charge that leaks onto that leaks out of the
yes.
Well, you can think about a capacitor as a conductor when it's empty, and then when it's full, it doesn't conduct.
Okay.
Either way, it works. So this way is I don't really like it because unless you put this proper capacitor. Okay, for most of the reset pin for the MCUs, the reason you can only put a capacitor instead of pull-up because a lot of MCU actually including pull-up already. Except the default ones are kind of weak. So that's why you saw a lot of MCU design, they put like 10K instead. So make an external pull-up even stronger. Just for safety and caution. Because if you just put a capacitor here, it will work with no problem. As long as you make your circuit properly. Yeah. But since you're gonna use one extra components enemy for your button, right? I feel like the pull down pull up resistor way is more comfortable. Any question? All right, then that's so much for today.